Okay, so let's chit chat about that assignment from yesterday. And yes, I know there are a lot of people gone today. It's like this whole half the room is gone. And
Yeah, it's significantly more quiet.
But it'll be more peaceful.
it might be. Okay, so
Which direction?
here's like the loop.
And how
Okay, and
this
this
stands
diagram
being
that I
funny
tried to show you. And you have a current that's going in this direction, okay? And you want to make this thing spin like this. So this obviously will only work if there's a current. If there's not a current, you can put all the magnetic field in the world on it, it's not going to make any difference. So you basically want to use that right-hand rule and try and figure out, hey, which direction does that have to go? So because of the fact that you want this thing to spin where this side's going down and this side's going up, let me give you a hint. Your direction is either to the left or to the right, okay? Because that's the only way that's going to make that spin. So your answer to number 3 is either to the left or to the right, okay? Not up, down, it's either just left or right.
Are you okay if I say something?
I don't like it. I don't like
Positive or negative X, is that fine?
That's fine. Positive, negative X, that's cool.
Okay, that makes more sense.
Yeah, positive or negative X, I speak positive or negative X as well. Now, so all of your answers on 1, 2, and 4 should be no.
Wait, 1, 2, and 4?
1, 2, and 4 are all no.
Don't know. Mind the X.
The key is the justification, okay? So just saying no is not sufficient. Explain it. When you get to number 5, so I threw on number 5, what?
I can't do this today.
Okay. So on number 5, here's the basic idea, is that you're gonna take this loop of wire and you're gonna try and figure out a whole bunch of things with it. So the first thing that you have to figure out is the mass of the wire, which is gonna be density is mass divided by volume. I've given you the density. The trick here is you have to find the volume. Well, that's going to be your cross-sectional area pi r squared times L. But you have to use the entire length of the wire, just not 10 centimeters of it, because you have to have the entire mass. So that length needs to be 40 centimeters, not 10. So if all goes well, your mass in kilograms is going to be around 0.2, okay? Maybe a little bit less. So if that's wrong, everything is going to go wrong. Now, the next thing, you need to find the moment of inertia and say, hey, we're going to treat this thing as like a thin hoop, even if it's a square. We're going to say, okay, we can model it as a thin hoop. So if you model it as a thin hoop, and I equals mr squared, and so a quick review, when you deal with moment of inertia, what are the only 2 situations you can actually use mr squared? Thin hoop and point mass, okay? So like for example, if I take this rubber stopper and swing it around over my head, that would be a situation where the moment of inertia is mr squared. The moon, you all did that calculation. You found the moment of inertia of the moon as it goes around the earth, okay? So your moment of inertia should start with a 4 and should be something times 10 to the negative 4th. Then you can find your torque, okay? So you can find your torque. Then, and basically to get that torque calculation, you're going to use the equation that you found up there at the beginning on that multiple choice question. So your torque should be something times 10 to the minus third. Okay? It's a pretty small value. Then from there, you have to remember that torque equals two things. It equals force times radius. It equals I alpha. I alpha. Okay? So your angular acceleration would make a decent GPA. Okay? Not horrible, not bad. And then your final answer on number 5 should be between 5 and 10 radians per second. So make sure on number 5 that you've kind of broken that up, Sean. Do not just randomly write things down and think I can follow it, okay? Bad, right? Break this up, Sydney, so that it doesn't look like one big Sydney writing storm happened.
It does.
It does?
Yeah.
Okay.
It's not terrible.
No, she tried to follow.
Like-
If Jaden looks at it and goes, it's bad, it's bad. Okay? I'm just telling you.
This thing is killing me.
Okay. So on number 6, okay? So this is kind of a cool thought that you have a wire carrying a current, and
There you go.
then you're going to have another wire underneath that you want to suspend it. So let's look at this. If you're going to suspend it, what force do you have to overcome?
Force of gravity.
Yeah, so you got gravity pulling it down, right? So there has to be some upward force to balance that out. So if you want two wires to attract, do you want the current going in the same direction or opposite direction? Same. There are certain things you need to know without hesitation, okay? So currents going in the same direction attract, and this is the opposite of about everything else in nature, okay? About everything else in nature, if you have a North Pole and a South Pole, oh, those attract. If you have positive and negative charges, those attract, okay? So about everything else in nature likes attract. With wires, it's just the opposite. Likes actually attract and not repel, okay? So just keep that in mind. So your answer on number 6, to get that amps, that should be, what did I say, something around your age?
A bit less.
Yeah, a bit less than Sean's age. On number 7, your 7 is just fairly a straight plug and chug, because it wants to know the maximum and minimum torque exerted on the coil by the field. So your torque is NIAB sine theta. And hopefully this makes sense, okay? So N is the number of coils. The more coils there are, the more torque is going to be generated. Everything, yes,
Is that equation just for the torque on solenoids?
yes. And again, if on the test, don't flip out and go, oh my God, I've got to memorize this. If you need this specific equation, I will give this to you. So I is your current, A is your area, B is your magnetic field. Okay, well, cool. Well, if your area gets bigger, that's going to imply a bigger torque because area is a function of radius. Oh, radius is getting bigger, okay, more torque. B is your magnetic field. Okay, if you don't have a magnetic field, you're not going to have a torque. And if you don't have a current, you're not going to have a torque either because you have to have both in that equation. And they're both directly related. The more current you have, the more the magnetic field is. That's going to create more and more torque. So your answer to that maximum torque would make a not so good GPA. Fairly, I guarantee you nobody in this class has probably ever had that GPA. And so what would be your minimum amount of torque? 0. Okay. And that's when the sine would equal, what would the angle be?
So just,
Yeah. Okay, on number 8, So, here's your wire, and the current's going in this direction, 2.5 amps, and you have a wire down here, okay? So, you kind of need to think this through in terms of external magnetic fields. So, you've got that wire up there, the current's going in that direction. So what's the bottom loop going to experience? Dots or X's? That whole bottom loop is going to experience X's. Okay? So now, if you use the right-hand rule, and this is a process that you need to be able to do. So if I use, I guess I'll keep writing with this. I wanted to change colors. Hi, Jane Girl. So, if you use the right-hand rule again for this top wire, that current's going this way. You run your finger this way, the magnetic field is going into the page, so what's the top wire going to feel? Attraction or repulsion? So the top wire is going to get pulled up towards the wire that's up above. In the bottom side, the current's going this way. So again, current's going this way, magnetic field is going in, the bottom wire is going to feel repulsion. So you're going to have the top wire getting lifted up, you're going to have the bottom wire getting lifted down. What about your sides? Nothing. Why? Yeah, so the magnetic field is going around like this. It's parallel with that magnetic field. The sides won't. The sides aren't part of the story. So basically, what you've got to find is the net force between those. Well, how do you calculate the force between two wires? Well, E naught I1, I2 over 2 pi, and there's an L in there. So, if you look at this, the I1 and I2 are all going to be the same. So the only thing, there's a D in there. So the only thing that changes is that value of D. So if all goes well, and you can calculate these separately, or you can do some fancy math and factor out a bunch of stuff. But that net force should be something times 10 to the negative 6th.
Bad GPA?
Yeah, I'll give you that. I'll give you that. And your answer to number 9 should be around 100.
What did you get? What?
Are we good? That,
On number 1, if you put like a magnetic field oriented in the z-axis, why would there be a torque applied to it? Is it because of the axle in the middle?
yeah, well, part of it is just the way that you want it to spin.
But wouldn't there be a torque on every side?
No, because some of them, if you're talking about sending it through the z-axis,
Yeah, the magnetic field.
yeah, there would. But it wouldn't spin because it would be like, so if you do it on that z-axis, then you'd have to do like that, okay, let me draw it out.
But so there is torque on all.
Yeah.
Hold on. So, here's your wire, right?
I'm confused.
And you're saying we're gonna send one up like this.
Yeah.
And the current's going like this. Okay.
Yeah.
So, if you've got that current going that way, like this,
Yeah.
and your magnetic field's going up, then that's going to pull this side out.
So they're all going to be pulled out?
Now, if you do the same thing over there, okay, that current over here and that current going up, what's going to happen? So can you make it spin?
I should have everything, so I think it's.
Oh, what it's gonna try and do is, it's gonna try and stretch it out, but it's not gonna make it spin.
So is it not torque because it's not being exerted over
So,
distance?
or would it just?
So I didn't hear what you said.
So would it not be considered torque because it's not being?
Yeah, well, and it's just not making it spin. That's the whole point, is that you're gonna try and make it spin about an axis.
That's not
rotating, so.
Yeah.
Thanks.
Will there be
Well, you
forces?
said,
Yes.
read my
It's
work
just not
and
gonna
do
make it
it.
spin.
Oh, wait, okay. You have to find
Okay.
areas, okay? Yeah,
Anything else? Abigail.
and you ties it by the.
Okay.
Yeah, chords. It
So
was mostly the area.
here's what I'm asking on number 4.
Yeah.
Says, 4 says, does it make any difference which side of the square on the Y plane is chosen to determine the direction of the field? So, if, because of the way that you want this thing to spin, okay, because you want it to spin about the
Sorry, I was
Y
gonna go
axis.
with this, I probably will find it.
So, here's the point, is that if you look at how this is gonna play, so, let's say you pick this side, and you put your thumb like this, the magnetic field is tough to do, it's going out like this, and so, that's gonna create a torque this way. But if I do this one over here, and go, and the magnetic field, if I'm going like this, the magnetic field like that, that's gonna push that down. So,
Yes.
here's my
Oh, yeah.
point.
So,
Depending upon which side you pick, it's either gonna make it go up or it's gonna make it go
the
down.
pie.
So that's why I said it doesn't make any difference.
Diameter.
You're still going to end up with that same torque, it's just whether you make it go up or if you make it go down. Okay? All right. Anything else? Once, twice,
So then,
magnetic field, sold.
yes.
Okay, for those of you that are watching this on YouTube, we're done. We're gonna watch some cool videos, but I can't technically rebroadcast it because it's copyrighted, so. Jay Carroll, I need some